All right. It's about one after the time to start, so I guess I've waited long enough, especially since attendance is optional. So, anyways, today's lab is the motion detectors lab. We've called it motion sensors, we've called it motion detectors. So if you see those other titles floating around, that's perfectly normal. It's just a matter of we've changed the name of the file, and sometimes the title inside the file will be different than the name of the actual electronic file and stuff like that. So just know that's going to happen pretty much every lab this semester. Uh, and again, this is for the online lab of 241 section L01B. But again, today we're using the lab called motion detectors or motion sensors or some other names. Anyways, the main thing is that lab is based on us using a little ultrasonic transducer. And that ultrasonic transducer would basically send out ultrasound waves. You can even slightly hear them, even though it's technically ultrasound. You can hear a little clicking going on when it happens, but it has this sort of little gold face and it sends out these signals in a cone from the actual sensor. It sends them out in a cone, and the manual says the manual for the actual device says that you can't really do much measurement closer than half a meter away. So you need to be around 50 centimeters away from the front of the detector. You also, of course, need the body of the detector in principle to run parallel to the actual, or I should say, the body should be perpendicular to the path so that the path that it's actually detecting is going straight towards it or straight away from it. Anything slightly off angle like that would give a slightly smaller reading of velocity. This is exactly the same reason why radar guns ideally are best used when it's as if the person driving the speeding car is hitting directly towards the laser, or excuse me, directly towards the dang it, I just lost directly towards the uh, radar detector. So, yeah, the detector basically. So, in other words, when a police officer says, "I've got you going over 55 miles per hour," uh, I've heard people use that as a joke. They say, "Would you call it 56 or something along those lines?" But in reality, the fact is they're saying it somewhat articulately to say that my device, my radar detected you going 55, and best case scenario, you're going right at 55, but more than likely, because it's very unlikely that he's got the angle for the radar gun set up exactly parallel to your path, in which case your velocity would be a little bit higher than 55, but it's been reduced down to 55 because the component of the velocity parallel to the line between the car and the radar gun is the only one that it can measure. So again, the component of the velocity, which we'll learn about vectors later, and that word component will make more sense, but the component of the velocity parallel to the line connecting the speeding car and the radar gun, that is the velocity that the radar gun detects. So it might detect 55, 55.2, or whatever. I don't even know. All the ones I've seen only have to the first whole number. So not necessarily a detector that reads to the nearest tenth of a mile per hour or something like that. So, anyways, that's what this motion detector lab is about, specifically using this motion detector device. As I said, it sends out a cone, and that cone can only really pick up data that well if it's no closer than about 50 centimeters away and no further than about 3 meters, if I remember correctly, 4 meters, somewhere around there. So that's the stipulations we had to make when we were actually making the lab. Now, during the pandemic, we were able to actually take this lab and render it in a form where we could just upload it, and then students could do the analysis portion, which isn't quite as useful from a experimental standpoint, but in some sense, the motion detector lab wasn't that wasn't really using that much experimental skills anyways, because you're literally just using a device that's already made up to do all the detection and all that stuff, and it automatically even spits out the graph for you. So the main thing is know that that's what we're using is this ultrasound device. It's going to make very specific graphs, and in the procedure for for the lab, it tells you many times to try to predict what you'll see. And in the spirit of actually learning the physics, it's best that you do, in fact, predict those things and even commit them to a drawing of the graph and then look at the actual graph data that we're providing. So if you look in our week 2 module, you'll see not only the write-up, which is called Sequence 1, Lab 2, Motion Detector, something like that. And then the addendum, which will say, Lab 2, Motion Detector Addendum. I think the one I put was the one that has a WTY in it because I made certain altercations to it. Uh, alterations. I don't know why I said altercations. I put certain alterations into the file to account for the way my class is taught. So you'll check that out as well. And what that addendum does is tells you how you're going to implement the actual lab that you would otherwise have done in the lab environment, but now you're doing it at home. And again, like I said, you will not be really doing the experiment. You're not actually, sitting things in motion and then waiting for the detector to detect their velocity versus time curve or their distance versus time curve. But that's the key to this lab is really more of a augmentation to the lecture because it begins to teach you what position versus time graphs look like, what velocity versus time graph look like. And in fact, you could even extend it to acceleration versus time. So another note to mention is I just said distance versus time, velocity versus time, and acceleration versus time. I want everybody to understand that when we say that, what we're saying is y versus x. So when I say a distance versus time graph, that means your vertical axis should have a distance or a position plotted on it, and the horizontal axis should be time. Okay, same thing with velocity versus time. That should have a velocity versus a velocity axis that's vertical, and then a time axis that's horizontal. And then an acceleration versus time would mean an acceleration axis that's vertical, and then a time axis that is horizontal. So those are the types of graphs you're going to do, and that terminology, that y versus x terminology, will continue and should already be somewhat familiar to you from your years of math. But the main thing is keep track of that. When they say A versus B, the first thing before the word versus has to go on the y-axis, which is understood to be uh, the data that is constrained to some extent. And then the free data is what's on the B, which is the word that follows the versus. So remember, A versus B. A is the dependent variable on the y-axis and occurs before the word versus, and then B is the independent variable and occurs after the word versus and is on the horizontal axis. But again, your job here is to make some understanding, get some understanding of what position versus time graphs look like. So, for instance, the key parameters of graphs are generally, intercepts and slopes and stuff of that sort. Where does the graph hit the y-axis? That would be called an intercept. If you said where does it hit the x-axis, that would be called an x-intercept. But y-intercept is normally just called intercept, but it still can be called the y-intercept. Curves, of course, can occur. And here, all your velocity versus time graphs should be straight lines, period. Okay, straight lines does not mean necessarily horizontal, but it could. Okay, so it could be vertical, it could be diagonal, it could be horizontal. If it goes as you move from the origin, if you go from the origin to the right, and then you go up, that should be what we call a positive sloping line. And if you go from the origin, say, to the right, and then have to go down to find the line, then that would be a negative slope. So you want to think about these graphs in terms of slopes and intercepts and stuff like that. So for instance, when you have a distance versus time curve, in principle, for a constant acceleration, you could have an actual parabolic curve. So in that case, you want to think, okay, well, what is the significance of where that graph hits the y-axis? Well, that graph hits the y-axis at t equals 0. So clearly that means whatever the initial position was, that should be the intercept. And then as you go along this curve, it will change its slope. And does the increasing or decreasing slope matter? Is the fact that the slope is positive, does that matter? Is the fact that the slope is negative, does that matter? What about a really steep positive sloped line? What about a very gradual positively sloped line? Or what about a very steep negatively sloped line? What about a very gradual negatively sloped line? And specifically, what does the height above that horizontal axis mean for each particular point? So, for instance, in a distance versus time graph, if you go up from any spot on the horizontal axis, which is time, then that distance up on a distance versus time graph is really how far it is from the detector. Whereas if you did a velocity versus time graph, then that distance from a horizontal axis to some dot on the line, that indicates the velocity at that particular time. Uh, Steep velocity or slope should mean something related to how fast the velocity is. In other words, how big the velocity is versus non-steep, which should indicate something about how small the velocity is, that sort of thing. We are using the word velocity here, and that's going to later be learned that is a vector quantity, and vectors, just like they said, Despicable Me, have direction and magnitude. So the direction, at least in these one-dimensional graphs, is indicated by whether the slope is positive or negative. So a positive slope on a velocity versus time graph. Notice this is important to say which graph, because the slope on a velocity versus time graph is not exactly well related to the slope on a position versus time graph. But on a velocity versus time graph, a positive slope means that the device is measuring a velocity that's going away from it, and a negative slope indicates a velocity that's going towards the detector. And the steepness, of course, should matter. And I'm trying to not give you as much answers about that so you can better understand it. So hopefully these words are helping you, but I know it's not easy for people to think about graphs and working out math in your head and that sort of thing. So it's not really very good for me to continue on with that discussion very much. So I'm going to go ahead and share my screen and open up the actual document so we can get a better idea, or you can get a better idea of what I'm talking about. So let me go ahead and share my screen. Okay, you should be looking at our PHY241L02B uh, Canvas course. You can see, of course, this is last week's lab. That was, of course, due this morning, or I should say, yeah, due this morning at 11:59 p.m. Generally speaking, that is the case. When we have a lab that I record at noon on Tuesdays, I post it shortly thereafter. That means you're supposed to have that lab turned in before noon on the following Tuesday. So keep that in mind. But anyways, that should have been turned in already. Now that I have met the deadline, I will immediately start grading it and give you very specific feedback on that lab about your lab reports. And I'm going to make sure I take off, 5 points for every little nitpicky mistake that you make, specifically not to hurt your grade, but to teach you exactly what I expect of my lab reports. So remember, you can always read what I expect in the lab report in my syllabus, and a shortened version of that description is in the Lab 1 Introduction to Lab, this little thing right here. It's also in this week's lab, which is right here, Lab 2 Motion Detector. Okay. So if you click on that, what you'll see is, again, this is a somewhat a shorter version of what's explained in the syllabus. In some sense, it's actually longer, but again, if you have a contradiction between what it says here and what it says in my lab, let me know, for starters, that that's a contradiction, and I will address it. But two, trust what was on the syllabus until that is corrected. Okay, so this describes how you're supposed to do your lab report. Remember, you start off with the lab write-up, which is a Word document, and you're going to start inserting the data and stuff like that. If you're typing any of that data into that Word document, of course, the font you use has to be different from black and easily discernibly different from black, so that I can tell what's been added versus what was originally in the write-up. So make sure you do that. Make sure you do all the insertions. For instance, if there's a calculation you had to do, any type of calculation you have to do, you have to show me one of each type of that calculation. And the best way I say to do that is to do the calculation neatly with, handwritten with pencil or pen, and then take a photograph of that and insert it into the Word document exactly where you were instructed to make that particular graph or that particular calculation. In this case, we were talking about calculations, but the same thing goes for graphs and data and so on. So anyways, this is where you'll turn it in. You can see it's due. I put 11:59 a.m. Because if I could write just noon, that would be great. And I'm not sure I had the ability to do that. So because I know some students get confused as to 12 a.m. versus 12 p.m. being noon versus midnight. I want to point out that 12 a.m. is midnight, and that's because it's ante-meridian, and ante is Latin for before. So it's before the sun crosses our meridian. And then 12 p.m. Is post meridian, which in general should mean after the sun crosses our meridian. But it's often literally exactly the time that it crosses our meridian. Again, meridian is a line of longitude that runs from the North Pole of the Earth down to the South Pole of the Earth, and your meridian is the one that happens to be directly under your feet at any particular time. Okay, so hopefully that helps. Now I'm going to go back to the modules, and I'm going to open up the motion detector lab itself. And actually, I might even be able to. I thought it was, no, that was something else. Okay, I thought I'd already opened it and left it open, but I didn't. So let's click on this so you can see what the lab is. It says Lab 2 Motion Detector. You can see, for instance, that the file that you clicked on did not have this 2019 in it yet. When you click on it, it now says that's the name of the file, and you can download it by clicking this button. That's what you want to do. Each of you want to have a copy of this so that you can then fill it out. But you can then see that the title is actually just Motion Detector Lab 2. This is the equipment that you would normally be using, but in this case, we're doing just the analysis portion. And at the end of this lab, you'll see there's actually a quiz, and that quiz is really the crux of a test on your ability to understand what you've encountered in the lab. So I want you to do it as perfectly as you can, but I also want you to interact with your lab partners so that once you first make your own hypotheses about lab predictions and stuff like that, as the quiz is asking, I want you to, of course, make an attempt at answering that first and then discuss it with your fellow lab students. I suspect you could, for instance, trade off emails, addresses, or phone numbers, or something like that. I've even had students sometimes make up Google Documents or meetings and stuff like that. You can do that. I do recommend you not necessarily do it by yourself. You're welcome to. That's the nature of this lab, but really you should be interacting with other people so that other people have a better chance of correcting your errors, and they have a better chance of you correcting their errors. So if you get in one of those ruts, then you'll have to think it out and figure out, what is the right answer. So please take that quiz at the end very seriously. It's not going to be in this sense that, or I should say, that quiz is not going to hugely affect your grade, other than the fact that, if you just don't do it, there's going to be a huge number of points taken off. But if you get wrong answers, uh, I'm going to supply the correct answers, and I'm not going to focus too terribly much on taking points off for the wrong answers in that quiz. But I certainly will take off if I find it's just a blatant error that you should have known better. I occasionally take off for that. But the real deal is that is mostly for you to make sure you learn the material. So please do your best to get it as correct as possible, but don't stress out that it's going to make your grade horrible. Worst case scenario, you really poop the bed on one particular aspect in the quiz, and you write something that's really off the wall, and boom, you lose 5 points. So it's not going to be that big of a deal. All right. So it does tell you some things that are very important here, and my students here usually miss this when I teach it in class. So I'm going to go ahead and read over it again in hopes that you guys will not. It says the fluctuations must be smoothed out and the regions that are not of interest must be eliminated. Idealize your graphs. All lines on the distance versus time graph should be either straight lines or smooth curves. So all of this that you see in this graph here and this graph, that's crap. Okay, that's not good at all. You do not want to turn in that. I mean, it's okay to turn in the actual or to show me that the actual graph that was made looks like that, but when you go to draw it yourself to interpret it, you should idealize it by this looks essentially like a straight line with some hiccups, so you represent it that way. This looks like essentially a horizontal line with some hiccups, so you'll just draw a horizontal line there. So that's the key point, is to make sure you idealize your graphs. Uh, you don't necessarily have to talk about, numbers on here, but sometimes it's helpful to say, let's call this time T1 and let's call this distance D1. And then if you go over here, let's call this time T2 and this distance D2. That sometimes comes in handy when you're trying to fully explain exactly what a graph looked like or what a graph was showing. So feel free to use that terminology, but don't think too terribly much about the numbers that would be on the vertical axis or the horizontal axis, because that varies literally from student to student when they were doing the lab, and you're just given a particular set of data that we, the faculty, ran for you. Okay. So don't write the numbers from the axis on your idealized sketches. You're only looking for trends and relative steepness of slopes. I would say the relative steepness of slopes, but I'd also say the intercepts are sometimes relevant, and the height of a particular data point, let's say that little data point right there on that line, that's a single dot is what I'm referring to, and the height above the axis tells me something about that. Similarly, this is a single data point on a distance versus time graph, and the height tells me something as well, as does the slope. So if you, for instance, compare two lines and one has a slope like this and the other one has a slightly higher slope like that, then you probably want to exaggerate that a little bit so that you can clearly see that one has a steeper slope than the other, because that steepness tells us something compared to the other one. Okay. So these are all the procedures. It's telling you a lot of setup stuff, which you, of course, don't have to do at all. It tells you notes, like I told you about the 0.5 meters. It tells you how to store the data, how to alter the graph, scaling variables, zoom, slope values, so on and so forth. Later on, we will be doing a lab where you'll download some software to be used on your computer, but this lab, you're not required to do that. But do read all of these notes and setup stuff just so you'll have some familiarity with it. Once you get through that, now we're finally into the procedure process, even though they didn't necessarily write the word procedure. There's the word procedure. I knew they had written it somewhere. So the procedure, of course, is here, but we're actually getting into the procedure parts here. And one thing explicitly that the addendum tells us is when you get down here to number 4 on page 4, there's page 4, there's step number 4. It says on the graph labeled prediction, draw what you think a graph of the following motion might look like. A person starts at the 1 meter mark, walks at a constant slow speed away from the detector, then stops at the 2 meter mark for 4 seconds, and then walks quickly towards the 0.5 meter mark. After drawing your prediction, set your time axis to 15 seconds by clicking on the button as shown, and then perform the experiment recording your results. Obviously, you do draw your prediction, but you're not going to do any of this set your time axis and stuff because we're giving you that data. But the important thing is to make sure you write this prediction down. And notice they gave you very specific numbers. And despite the lab manual saying specifically, where is it at? There it is. Don't write the numbers from the axes on your idealized sketches. This is a case where drawing in number 4 here, drawing the 2 meter mark and the 4 second mark and the 1 meter mark and the 0.5 meter mark, all that stuff. Those actually could come in very handy here for you making a very precise prediction, and that's what I want you to do. So do include those numbers there, and feel free to use them, even though, like I said, the books just or the manual write up, whatever you want to call it, is just trying to keep you from avoiding using the numbers, which we didn't take any time to calibrate or anything like that. But when you're trying to make a prediction specifically about when something occurs, then those times would be extremely helpful, and those distances away could be extremely helpful, or the actual speeds at particular times could be helpful. So you'll go on through, and then they ask you these multiple choice questions like the slope of the graph is A, a constant positive value, or B, always positive but becoming steeper, C, always positive but becoming shallower, more gradual is another word for that, or D, starts positive but begins negative. So you've got to choose one of these choices, and if there's marks on more than one, I'm automatically going to mark that you got the answer wrong. So don't be hedging your bets. You can choose to put a box around it. You can choose to change the font to say red or blue. And if you do that for only one of the choices, then I'm going to assume that that is your answer. So make sure you do that accordingly. Don't mark multiple answers ever. Okay. Or if you do by accident, then make sure you clean it up as much as you can, and even write some text saying, hey, I'm saying the answer is C, despite the marks on A and D or whatever. Okay. It says produce graphs similar to those below and indicate what kind of motion was required. So you're producing graphs in some senses. In this case, is completely imaginary. We would have liked you to walk towards the detector or walk away from the detector and speed up or slow down or stop at a certain distance away and stay sitting still. All of those things are kind of things we would have you do in front of the motion detector, and then the motion detector would give you the actual graph of your data and the specifics about you. And that's what you're really trying to get an understanding of. So we have graphs that we've already made for you to analyze, and you'll see them in that module for week 2. Okay, here's walking velocity versus time. Notice these D's on the vertical axis mean these are distance versus time graphs, but you could also call them position versus time graph, because you could imagine instead of the motion detector just detecting how far away something is, you could imagine the motion detector being the origin of a number line, and then the actual distance away is not only the distance away, it also happens to be the position on that number line. Okay, so keep that in mind. That's something that you should be thinking about when you're graphing these things. Again, all this stuff where it's telling you to maneuver to folders and open up certain in this case, electronic files, that's not applicable to you guys, as you'll see in the addendum. But as you get through, notice there's a lot of questions you're answering throughout the lab, and you really want to learn those. And this is, even though this is the quiz part, this is still something that would help you interacting with another student. So please, by all means, try to get with another student in the class so y'all can work together. If you can't, let me know, and I will see if I can find someone that's willing to work with you. And probably there'll be multiple people that might ask me. So if you do need that, let me know, and I can just, clear a way to make sure permissions are granted to give each other's email or phone numbers or something. But really, you might want to just show up in one of the recorded lecture sessions, which for instance today will be one at 5:20, and then you can exchange it with some individuals in the class. Okay, but do remember, answer all these questions. I do take off 5 points for every one you miss, so pay attention. uh, Here's some other answers. Here's another question as well. Here's another question as well. Here's another question as well. And here's a bunch more questions. These are all really, really good, thought-provoking questions that you need to do uh, to actually answer. And it's important that you answer them first and then talk to someone else about them to see if they agree with you. And then you two sort of hash it out and see what's right or wrong. Ultimately, I'll be providing answers for you. Okay. Of course, as soon as I actually supply those answers, which is usually right after the lab is due, then I basically you can't turn in a lab at that point because it's just, you could literally just take the data that I gave you from the corrected lab and just put that back in. So I'll accept them, but they're going to be huge deductions. Okay. The bare minimum is 5 points for turning in something late. But it can be often a bit larger if it's after I've already posted the corrections to it. So make sure you don't do that. Here's some more questions, and then summary questions. And here is the summary. And this is sort of the quiz that I was talking about. The summary is the quiz that I was referring to. Next one, it'll literally be called a quiz. This one they call a summary. But you want to draw on here velocity versus time graph of a constant slow speed toward the detector. And then we want you to do the same thing for a distance versus time graph. Again, slow speed walking toward the detector. Okay, so on and so forth. All these questions have to be answered. And notice this is one of those where there are multiple selects, so you got to pay attention to that. All these graphs are individual choices, A, B, C, D, E, F, G, H. So that's what they're wanting you to write next to this. So the movement was always in the same direction. Maybe you think it's E and B, so you put E comma B here. Again, you can type that in if you want, or you could, write it in handwritten if you have a document that, but I'm trying to avoid printing as much as possible. Okay. All right. So that's the end of that lab uh, write up. So you know hopefully what to do with that. Now what I'm going to do is I'm going to go back to the week 2 module. I'm surprised another one hasn't popped up yet. I actually copied it from the other one. What I want you to see is the addendum, which makes it a lot simpler, okay, than what you normally have to do with this lab. So let's just let this load up real quick or real slowly. Okay, this is taking a really lot longer time than I expected. We have a student that's coming in. Hi, Zach. As mentioned before, your whole name will be on the internet when I post this on the video, unless you want to change that username to just, your first name and your last initial or something like that. I don't know why this is taking so long. Let me try loading it again. No, that's not helping. Okay, let's go back and try clicking on it again. You might actually have to just download the document to read it, specifically because it's a docx, which means it's the latest version of Microsoft Word. So Canvas might be having a difficulty opening it. But again, what I'm referring to is week 2, the motion detector addendum. See if it opens any quicker. Oh, finally. Okay, so lab 2 motion detector, Mr. Younger's version. This lab will follow the lab write-up exactly. The only difference is that you will be given the graphs for each section instead of producing them yourself. On procedure step number 4 on page 4 of the lab, please attempt to predict what the graph will look like before looking at the graph that is included. This eureka moment of prediction and then getting feedback is a big step in the learning process. We know pedagogically, meaning the science of how we educate in some sense, dictates that you discovering, after making a prediction, you discovering you're right is pretty good, but even better is when you discover you're wrong by making a prediction and then seeing the reality. That is a very valuable learning experience, and allows it to become internalized a little better than just someone telling you what the answer is. So keep that in mind, not only obviously when you're solving or not only when you're doing this lab, but also when you're solving physics problems. Okay. When you are filling in the graphs on page 12, please use pencil to draw the graph. Take a picture of your drawn graph and paste that into the lab right up immediately after number step 4. Remember that all the graphs will be either straight lines or smooth curves. And I'm specifically talking about that particular graph, but all the other ones you should be putting them as explained in the syllabus. You should be putting the graphs right where they ask you to make them or where they tell you to make them. So do that. But that's literally the whole addendum there. Now, while you're here, I'm going to go back to the modules and then I'm going to upload the individual graphs. So let's open up these files. And in this case, I copied everything to this course, but it's still not in. Yep, it's still not in yet. So instead, I've got to pull them up from my folder hierarchy, which luckily I had in place because I knew this could happen. So I'm going to upload these files. So there is, I really want to look at this to know the order. I would like to put these in the proper order, but uh, I can't do that without having the other one in place. But I think you can figure out what they are because they basically are numbered. So let's put this here. There's 10 files that are going to be uploaded. Okay. And now you can see all of them are in here. In fact, this one's a copy of the one immediately below it. I accidentally did that twice, so I'm going to go ahead and delete that guy. Okay. But you can see it looks like air track 3, level track down and back, air track 4, incline up and back. And then, of course, you have 2 and 3, and then 4, slow away, stop, 5, walk away while speeding up, so on and so forth. So those are the files. It should be pretty obvious exactly which files for which part as you're going along doing the lab, but that's it. That's all you've got to do. Does anyone have any questions? You can feel free to type that in the chat window if you don't have audio. I just opened the chat window. Zach, did you have any questions? All right. You weren't here when I first. Oh, yeah, gotcha. You weren't here when I first started, so just in case you didn't know, I want to remind you. I try to do these at noon every Tuesday for lab, and then I try to hold my lectures at 5:20 every Tuesday and Thursday for this class because all of this is I'm treating it like it's an asynchronous. It's definitely an asynchronous lab, but I'm treating the lecture like it's an asynchronous lecture as well. Even though, let's see, I want to double check, make sure that it is what it was. This okay. Technically, the 241N02B is not a asynchronous lab, but like I said, I don't take off points for not showing up, but I will advise you, not being there in real time and not getting help in the lecture portions is really, really, really difficult to do well in this course doing that. But anyways, this lab is definitely asynchronous by the books, and I always treat my online lectures like they're asynchronous, where I don't really harm students that can't make it in time, but I just warn them that it's very, very hard to succeed if you're not attending and interacting with me during lecture. Okay. All right. Well, that's it. If you don't have any more questions, I'm going to go ahead and call this a day. We're done with the lab write up or with the lab explanation portion, and I'm going to be posting this to YouTube, my YouTube channel, really soon. Zach, do you know where my YouTube channel is? Have you been to that and everything? Again, you can type it in the chat. Okay, cool. Good deal. All right. Well, that's it. I'm going to sign off. Thanks for coming. I do appreciate anybody coming. And like I said, this is always an office hour for you, at least once I finish. So like I've just finished and it normally takes me about 30 minutes to introduce a lab. This time it took me about 40. That's okay. But the main thing is once I finish that part, the rest is just open for you to have any questions on lab or lecture. So, uh, I'm going to wait for the last person to leave and then I will leave. So you're free to go. Thank you for coming and hope you have a good time. Now let's look up, see what's going on here. Okay, everybody has now logged out. So I'm going to call this an end. Thanks, everyone. Bye-bye.